Ganymede is an enormous moon, larger than any other we've found, including our own, and may one day be the centerpiece of wider human settlements around Jupiter. Colonizing Jupiter's moon Ganymede presents a fascinating mix of opportunities and challenges that we'll be exploring today. As a basic background, Ganymede is the largest moon in our solar system, roughly parallel in size to Saturn's largest moon Titan, which is slightly wider if we include Titan's tall atmosphere, but if we just go by distance to surface, Ganymede is a bit wider than Titan and also modestly denser and more massive. Indeed, it is bigger than even Mercury, but being a good deal less dense, is a little under half of the planet Mercury's mass and a quarter the mass of Mars. It is also twice as massive as our own moon, though because it is less dense, gravity is a bit lower on Ganymede, 14.6% of Earth normal compared to the moon's 16.6%. In this regard, we tend to think of it as very like our own moon, only without the proximity to Earth, or the Sun, so it's often a less discussed colonization option than the major planets, or even moons like Titan with its thick atmosphere, or Europa with its subsurface oceans. But Ganymede has some unique characteristics that make it an interesting target for colonization efforts. Today, we'll make the case for Ganymede by first reviewing some of the key advantages and challenges associated with such an endeavor. Now, our moon again is mostly of interest as a relatively easy place to reach that has raw materials for us to use for a base, and which can provide fuel or materials for missions further from Earth. And the same is true for Ganymede, but while it is the biggest of Jupiter's moons, that's also something of a hindrance too, as it means more gravity. And while the gravity at the surface is weaker than our own moon, the escape velocity is modestly higher, whereas the other Galilean moons all have lower escape velocities. The Galilean moons, Io, Europa, Ganymede, and Callisto, in that order, are also just 4 of several dozen moons Jupiter has, although the remainder of which have trivial escape velocities that could be achieved with a rocket you could bang together in your garage. Indeed, for most, simple compressed gas would work. Unfortunately, most of them are not going to have ready supplies of ice to work with exactly because of that low gravity, and that is a big advantage Ganymede has. Ganymede has a significant amount of water ice. Indeed, we think it might have more water on it than all of Earth's oceans combined. While methane and ammonia are easier to work with as in situ fuel sources, water broken into hydrogen and oxygen to be recombined during combustion is a superior fuel in terms of specific impulse or maximum speed, and not only can water ice be used as a source of drinking water for colonists, but by electrolysis we split into hydrogen and oxygen for fuel and breathable air, and by a very simple and relatively low energy process. The presence of water is of course also crucial for supporting life and agricultural activities. Now this is also true of Europa and Callisto, and indeed ice is rather plentiful out in deep space, and both Europa and Callisto have a lot going for them as settlement sites as well. Indeed, part of what makes all 3 attractive as a settlement is their proximity to each other and relative ease of moving between them. This is why I often suggest that collections of moons around gas giants might be your natural alpha site for a new star system, rather than our default of looking for an Earth-parallel world in gravity and lighting that we can terraform. You can make fuel abundantly on all 3 of those Galilean moons. All 3 have modest, if significant, escape velocities, and the delta V and travel time between each other is also modest. Europa, Ganymede, and Callisto are all tightly locked to Jupiter, meaning one side of them sees Jupiter all the time as a massively huge sphere in their sky, while the other side never sees Jupiter at all. As a result, their daytime period is the same as their orbital period of 3.5, 7.3, and 16.7 days respectively. That means they all have a shorter day length than our own moon, and in Europa and Ganymede's cases, well inside what planets could handle for protracted dark periods. The thing is, Europa is very saturated by radiation from Jupiter, and we normally shrug that off because we're interested in exploring its subsurface oceans, not its surface area. Ganymede, Jupiter's largest moon, is subjected to Jupiter's magnetic field, which traps charged particles. This results in Ganymede having a radiation level significantly higher than Earth's surface. However, Ganymede is unique among Jupiter's moons as it has its own magnetic field, which provides some degree of protection against Jupiter's radiation belts. Radiation levels on Ganymede's surface are mainly from cosmic rays and charged particles trapped in Jupiter's magnetic field. The radiation environment is harsh, but not as extreme as on Europa or Io, Jupiter's other moons closer to the planet. Specific measurements of the radiation levels can vary. We need to get some probes there, but it's understood that the environment is hostile not just to biology, but also electronics. Now, we are not going to be classically terraforming Ganymede. It would have an easier time keeping an atmosphere than our moon, and we did discuss terraforming our moon a few months back, but the lower levels of sunlight and all that extra radiation don't make it as decent a terraforming candidate, and as we discussed in that episode, terraforming our moon would probably only happen because the moon is likely to be viewed as the biggest jewel in humanity's interplanetary empire, one on which vast resources might be expended for improvements. Though as we discussed in colonizing Jupiter many years back, while Jupiter is nowhere near massive enough to be a star, and its many moons almost represent a second smaller or more compact mini-solar system, of which Ganymede would likely be the crown jewel of that mini-empire, so maybe classic terraforming, or the hybrid of it we discussed in Terraforming the Moon, might be considered down the road. In the meantime, any base on Ganymede is likely to solve the triple problem of low temperature, low sunlight, and high radiation with the same approach. Big domes that concentrate light onto a smaller area, insulate to help prevent air and heat loss, and block out radiation. Ganymede's surface temperature is extremely low, averaging around -160 degrees Celsius or -256 degrees Fahrenheit. This extreme cold presents challenges for human survival, energy use, and machinery operation, and it means you want to operate under domes or underground whenever possible. I do want to emphasize though that the radiation on its surface is not super lethal. The figure I usually see for Ganymede's surface is about 0.08 sieverts per day, and we usually place the lethal level at 2 to 10 sieverts, 25 to 250 times that amount. And given that you would have to have something between you and that surface, which is very nearly vacuum, that spacesuit, vehicle, or dome would further decrease the dose you got. It is also very likely that humans on Jupiter would benefit from being in an era of superior medical technology for handling cancer or radiation sickness, possibly mitigating or even eliminating the concern. I would not expect human missions there until at least the late 21st century, if not the 22nd, which is a lot of time to improve medicine. In the long term, there are things we could do to further decrease the radiation incident on Ganymede that we have discussed elsewhere, including some mega engineering projects like limiting the particles in Jupiter's magnetosphere in the first place, or placing an enhanced artificial magnetosphere around Ganymede. But let's keep to the more near term in our discussion for now. Ganymede's surface is a mix of ice and rock, and plentiful in craters, so finding a nice spot to set up wouldn't be too hard. That rock contains plenty of silicates, so we can't easily make glass for domes, or mirrors, and one of your easiest ways to deal with radiation and micrometeors, as with on the moon, is just to do a thick and high roof on a structure and then have transparent walls or windows that have mirrors off to the side which could reflect light into that habitat. And those mirrors could swivel off those windows to focus light on solar thermal power generation during Ganymede's long day if you want to have some nighttime. If you are breaking its orbital period into an artificial single week of 7 24.5-hour days, where you have opaque your windows at nighttime when the sun was still out, you'd be able to arrange 4 of those days to have decent sunlight and 3 where you had to use artificial lighting. A week on Ganymede is basically one natural Ganymede day and year. Now, decent sunlight is a bit subjective. Like Jupiter, Ganymede is just over 5 times further from the Sun than Earth, and during its roughly 12-year orbit of the Sun, we'll be getting between 3.4 and 4% as much light as reaches Earth's atmosphere, which absorbs about a quarter of our sunlight before it gets down to us, including some harsh frequencies of ultraviolet. But that means essentially that it's between a 20th and a 25th as bright on Ganymede as Earth, and that is not dim, and would be equivalent to an overcast day here, and not a very overcast one either. Many planets could survive on that just fine, but it would make a lot more sense to be concentrating light onto them. Nonetheless, you do not need to concentrate 25 times the sunlight to get either healthy plants or comfortable temperatures inside a dome or mushroom-style habitat. Likely even a quarter of that would do. It is also very easy to erect towers on low-gravity airless planets, so putting mirrors on towers around a crater you want to dome and farm is pretty viable. This is assuming sunlight and solar power is your main way of getting light. Often when we contemplate colonizing around Jupiter, we are assuming we are mining the gas giant for fusion reactor fuel. This might be for deuterium or even regular hydrogen or helium-3, in which case you may circumvent the weak sunlight issue and surface dome's concern by simply having fusion reactors supply light by LED for crops and for heating homes, all safely buried under rock and ice protection. First, it is very likely that even if we get fusion working, it would not replace all other power supplies. The basic physics of fusion are likely to always benefit from bigger being better, so it might be something we can really only use on the very large scale for reactors supplying millions of people or for giant arc ships traveling to deep space. Second, fusion fuel itself is not terribly likely to ever be the lifeblood of trade, any more than water or air are for all their critical value. Even if we assumed we could only use isotopes like deuterium and helium-3 for viable fusion, not regular hydrogen or helium, it's still incredibly abundant. While only 23 out of a million hydrogen atoms at Jupiter are deuterium, that still means it has something like 40 trillion megatons of deuterium available, and just a single megaton of that would easily supply our entire planet's current electrical needs for several centuries, even at a low efficiency rate of mass to energy fusion and energy to electricity conversion. So you don't have giant freighters leaving Jupiter for Earth every day. Indeed, you probably don't have any freighters carrying deuterium to Earth from Jupiter because Earth actually has a higher concentration of deuterium in our ocean water than Jupiter's atmosphere has, and we have to work pretty hard to put a dent in that supply on anything less than geological timelines, let alone the period of early interplanetary economies we're interested in today. What's more, the reason Earth has a high concentration of deuterium is because it is slightly heavier than normal hydrogen. We used to have way more hydrogen when the planet was forming, and we've lost deuterium slower than regular hydrogen, because it is heavier and has a harder time escaping a planet. For similar reasons, a lot of the hydrogen in deep system objects like icy moons is still left over from hydrogen stripping processes that Jupiter's sheer mass gave it resistance to, so there's no shortage of deuterium in these places either. I just got done mentioning it would be hard to use up Earth's deuterium supply in our oceans, and earlier I mentioned that Ganymede is suspected to have more water than our oceans contain. And while Io is decidedly volcanic, the other two Galilean moons, Europa and Callisto, also have tons of water and thus tons of deuterium, all easier to reach than the vastly bigger but more diffuse supply deep down inside Jupiter's enormous gravity well. Since helium doesn't bond to much, we have precious little of it on Earth, but while Jupiter has plenty, indeed more than every other planet combined, it is not as accessible as the supplies on Uranus and Neptune, and if you actually have helium-3 fusion, usually referred to as aneutronic fusion, Uranus and Neptune are very easy to travel to. This was more or less the plot of our episode Colonizing Neptune. So the reality is nobody is mining Jupiter itself for anything in those early solar system days. It is where half the solar system's mass, not including the sun, is located, so one day it does get mined, but is basically the last place to mine because of its gravity well. And while we might mine those Galilean moons for deuterium and water and nitrogen among other things, it's not really for Earth. It's for local use or maybe shipment to the asteroid belt, Mars, Mercury, or Venus. And Mars doesn't need deuterium as it has tons of ice, at least for power extraction purposes. There's always that question of whether settlement of other planets and moons will tend to grow out from one or two bases that are cities, or if we see a lot of small outposts and homesteads, and a large fusion reactor able to supply millions might encourage the former, while being forced to concentrate sunlight for power might lend itself to smaller enclaves. Either way, some colony of 1,000 on Ganymede might have a fusion or even regular fission reactor, but my hunch is that they would not. Why? Well, on most objects in the solar system, there's no atmosphere, there's no wind or dust, So once you roll out some polished reflective metal sheet or parabolic dish, there's not much maintenance to worry about. It doesn't even need to be very sturdy because again, no wind, and virtually no gravity either. You could take regular aluminum foil and line a dish, shiny side up, and now it's a solar concentrator. You don't even need a dish behind it either, because it doesn't need the structural support. Indeed, even some dish made of ice would work, especially with a foil cover. So once you spend the energy to melt some metallic rock down into metal foil, you get a power supply good for half of forever. You might need to replace components the light was focused on, the actual photovoltaic panel or components in a solar thermal plant, but you can concentrate to a lot higher power on that panel than the solar noon here on Earth, and actually get a much better performance and lifetime out of that panel on Ganymede or wherever, because the absence of weather isn't just getting rid of that irritating fluctuation output, it's also cutting down a lot of wear and tear on that panel. Even more so if your reflective panels are not reflective to material damaging wavelengths like ultraviolet and bouncing that onto that sensitive panel. You'd also use the local supply of methane as a simple combustion fuel as a backup or mobile energy source, or use excess power to create carbon-neutral hydrocarbons, which takes more energy than they produce, but is often preferable to battery storage and serves those same backup and mobile energy functions. There's bound to be a lot of situations where a reactor will be better, and it's very dependent on the actual technology available. Certainly if someone cranks out some micro-fusion reactor that is rugged, cheap to produce, and in the power-to-weight ratio of a gas generator, then that's what everyone has. And I am hoping that is the future we get, and something like that could even happen this century. Sometimes when tech rolls out, it avalanches. Indeed, that's often the case, and if it is something that would be permissible under science and engineering, we might get there very fast once we make that first critical breakthrough. My hunch is that bigger is better for fusion, and that anything at the individual or even small community scale will be impractical unless we have ready access to antimatter to use for antimatter catalyzed fusion, which requires only small amounts so is not so dangerous for storage. On the flip side, there's definitely no bar under known science on making a machine able to melt down a rock and turn it into reflective panels or silicon wafers, and I'm betting you could make something the size of a modern generator in the kilowatts range that could unfold into a power collector and factory for inserting ore and spewing out the key components, with maybe smaller and more elaborate bits being brought in from a more sophisticated factory elsewhere, allowing you to build whatever size solar power plants you need. Once you have a power supply, access to raw materials, and some way to fabricate more power supply, you have everything you need for a self-replicating growth scenario, be that a basic biological cell, some clanking self-replicator robot, or a human with access to decent automation who is handcrafting their power collector from foil or plates made by their auto refiner from rocks they picked up and tossed in. This is the argument made by Dr. Leonardo Cormier, chief geologist of the first human mission being sent to Ganymede, launched June 22, 2153, and set to arrive on March 15, 2156. It's a slow trip, but lets them maximize their cargo, and they're going to need it. Until this point, every spacecraft sent to Jupiter has been a robot, and robotic attempts to land on Europa thus far, with the intent of probing the subsurface oceans there, have been unsuccessful. This is blamed largely on signal lag time and restrictions on AI. No AI smart enough to definitely get the job done is allowed under treaties, especially far from human oversight, and Jupiter is a light hour from Earth. Now the plan is to set up a permanent base on Ganymede that can facilitate the growth of more bases and settlements in the Jupiter area, including on Europa, where they believe they could carve in a facility under the ice for humans to oversee operations directly. But that is a Phase 3 project. Phase 1 was the launch of Cyclocraft carrying extra supplies in March of 2150 that arrived shortly before the crewed mission was set to launch in 2153 as proof of concept and to provide lots of redundant, bulkier supplies. Current launch philosophy is always to send supplies in advance on a parallel mission to provide redundancy, work out bugs, and potentially encounter some unknown unknowns that might endanger the human crew. Leonardo was selected for the mission shortly after that Phase 1 launch, as he was rather famous for being one of the original inhabitants of the moon, and one of the youngest, and often nicknamed by fans Lunar Leo. His family's efforts at exploring and settling the moon were made famous in the documentary Living in Lava Tubes, and while several of the crew for Operation Galileo are veterans of the moon or orbital operations, Leonardo does hold the title of Senior Spacer on the mission. While a lot of the crew are focused on the eventual Europa mission to melt through the ice and explore the subsurface oceans, Leonardo is here for the geology, and the Galilean moons represent 4 of the 7 largest moons in the solar system, and lunar geology is his specialty, and it will be critical to helping set up those initial mining production processes. Fuel production is the day one priority though, and will be overseen by the only Martian veteran of the crew, who helped improve the process at Planum Australe Base on the Martian South Pole. During the trip, the sun is eternally visible and slowly weakening as they head into deep space far from any planet's shadow, and they begin adjusting everyone's rhythms to the Ganymede week of 7 subdays lasting just over 24 hours each. Ganymede was chosen because it was seen as the logical first base, where communication to the other 3 moons would be relatively quick, but the radiation low enough to survive a good deal of early surface operations. They planned to use as many remote robots as possible, but wanted to know they could use humans if there are problems, and Europa's own surface radiation is at lethal levels in mere days. One upside is that humanity has gotten very good with cancer treatments, so they could probably survive continuous and multi-year surface exposure on Ganymede, but this does not mean anyone is anxious to get high levels of radiation, particularly as while they aim to be principally solar powered, they do have a nuclear reactor on the ship and plan to use it on the ground too. Operation Galileo and its 30 crew will begin by orbiting Ganymede in March of 2156, while they rendezvous with the cargo left in orbit in the Phase 1 robotic mission and confirm the primary landing site. During the initial landing operations, Leonardo is just another pair of hands helping manually move cargo or run robots, but he'll be active in later weeks of the mission once they've secured access to water and shelter. Leonardo's main job in base setup is not just finding ore deposits to make mirrors or storage tanks, but all the minerals they need for running hydroponics. Not just for their own uses, they brought some, but to get the process of extraction and refinement going by late 2056, as the Phase 3 ship carrying more crew and interlunar shuttles will launch from Earth October 1st of 2056 and needs to know what they need to pack. In their current estimates, in order to supply food, they need roughly 150 square meters of greenhouse per person, and 10 times that in mirrors to give sufficient sunlight for growth, for 45,000 square meters of reflective panels, and they need just as much for power, heat, and fuel production. They estimate they need something like 300 to 400 square meters of reflective paneling per person, or a 200 by 200 foot block, especially to add in extra capacity like algae as a feedstock for fuels and plastics. They have those in inventory, manufactured on Luna by time-tested processes, but those processes will have to be adapted to Ganymede. Part of their mission profile is to manufacture their own and get that rolling before Phase 3 has to commit on its final payload, and the same for supplies of silicon and various macro and micronutrients. But Leonardo can't do much roving until fuel production is up and running, so he is estimating he'll only have about a 1-month window to go out in his rover and investigate his list of candidate sites to find which ones have what they need and which combination is optimal for getting them all the resources their fledgling settlement will require. He is able to find everything they anticipate needing in large quantities in just 3 sites, all within about 10 kilometers of their base, and with fuel production running and those sites identified, Leonardo is free to explore Ganymede's ancient geology. He suspects this will easily keep him occupied till Phase 3 arrives, and is hoping to one day set foot on Io. Once Phase 3 arrives, their production of fuel and bulk materials on Ganymede allows reusable spaceships to move between the Galilean moons in a few days of travel. When it comes to sophisticated things, especially some items like pharmaceuticals that won't store well for multiple years of transport out to Jupiter, they have to balance how much they need to have that item versus how hard it is to manufacture it here with the very limited personnel and materials they have. But this is not a new problem, and one Mars and various asteroid mines have all had to work with, even if Jupiter has larger delays in transport. The Phase 1, 2, and 3 spaceships are all planetary cyclers that were dropping out the crew modules and cargo at Jupiter and continuing on very long elliptical journeys that will carry them past Earth and Jupiter in their travels and provide a slow, if low-cost transport system for durable goods and passengers going each way. Leonardo and the fuel export from Planum Australe are optimistic on being able to get cyclers going from Jupiter to the asteroid belt to help carry water and volatiles to the mines there, and to the fledgling colony floating on Venus's atmosphere, and the still-planned Mercury colony. In this way, they can help get Ganymede and the Galilean economy in general jump-started, and prove the spacefaring economy is possible without having to rely on Earth for eternal subsidy or as a primary client and market. So, how likely is this scenario? Hard to say, of course. It's very dependent on the tech. They might arrive at fully formed bases erected by machines, or just land a spaceship that was a habitat module and could just extend telescoping or inflatable segments for solar or farming, or dig in and run on fission or fusion energy. There's plenty of uranium in the solar system and probably on Ganymede, and we could imagine as a source for fission fuel for the outer solar system. Many of the solutions for living on Ganymede are those we'll learn on our own moon, and will translate to other deep system colony sites like other icy moons or dwarf planets. If the gravity is too low for humans and terrestrial organisms to adapt to, we find a crater or melt into some ice and set up a rotating habitat with sloped walls. On lower gravity objects, which are most of them, the gravity is so low a normal rotating habitat works fine, and you just embed it inside a rock for protection from radiation and meteors. But where there's already significant gravity, a deep bowl or vase shape dug into existing rock will generate higher gravity by combining spin and natural gravity. We can bring more light to Ganymede, or chosen spots on Ganymede, by use of orbital or Lagrangian mirrors, and in theory even add more gravity by adding mass drawn from Jupiter, or alter its orbital period to a nice multiple of 24 hours, or even break its tidal lock with Jupiter, using the techniques we discussed in the recent episode, Can We Terraform the Moon? Ganymede is the biggest moon in our solar system, and very close to 3 of the other largest, so it seems only natural we will settle it one day, and it would form a close relationship with those other 3 moons and the dozens of smaller moons nearby. They can supply the raw materials to build up a robust industry and agriculture to help fuel expansion in the asteroid belt and all those other worlds further out, and even to the Kuiper belt. And for that matter, it may not just be the moons of Jupiter that Ganymede helps build up and work with, but the huge floating extractors and refineries that will likely one day far away grace the upper atmosphere or lower orbital region of Jupiter itself, which, while hard to reach, still has more mass than every other planet and moon and asteroid in our solar system combined. See our episode Colonizing Jupiter for more discussion of that. But as we saw today, colonizing Ganymede might be one of the first and boldest steps out into settling space, and may not be too far ahead in the future. We joined some astronauts for a multi-year journey to Jupiter's moon Ganymede today, and talked about how they would need to bring in as little as possible on their ships and make as much as possible on site or in situ. And one example of things they probably aren't going to have room for is several years' supply of disposable razors. Cost might not be as big a factor there, but for us, you could easily end up spending thousands of dollars per person on disposable razors for that sort of mission timeline. I recently switched to a Henson razor as it just gives a better cut, but I've been using a safety razor for many years and never missed the drawers and garbage cans full of disposable razors waiting on use and emptying my wallet while filling the landfills with plastic and razor blades. All that gets tossed with a safety razor is one easily recyclable, cheap 10-cent razor blade. The reason why Henson gives a better cut is because they use precision manufacturing to aerospace standards. They helped manufacture pieces for Mars rover and the space station, so they get the importance of quality. This makes a razor where the blade fits in tight, and that stops the vibration and flexing of the blade that cause a lot of the irritation and razor burn people often get from shaving. That tight tolerance on the blade position, exposing only 27 microns of razor, also makes it easier to adjust to shaving with one if you're new to safety razors. Stop wasting money on disposables and elaborate 5-blade cartridges. One 10-cent blade is all you need if it's held in place by precision engineering like Henson Shaving offers. Try it now though at hensonshaving.com/IsaacArthur, and Henson Shaving will throw in a free 100-pack of razor blades if you use promo code IsaacArthur at checkout. Get a better shave at a fraction of the cost. Go to hensonshaving.com/IsaacArthur. So that's it for May. We'll be back June 1st on Nebula with a look at in-situ resource utilization, and on Thursday, June 2nd, we'll look at what sort of jobs in space and the space industry there are, both now and in the future. Then we'll return to the Fermi Paradox and continue last week's discussion on the nature of intelligence, to ask if our minds themselves may be a ticking time bomb waiting to inevitably ruin us. After that, we'll have a pair of episodes on oceanic moons, ones with surface seas, and paradise planets, places even better than Earth for us to live on. If you'd like to get alerts when those and other episodes come out, make sure to hit the like, subscribe, and notification buttons. You can also help support the show by becoming a member here on YouTube or Patreon, or check out other ways to help at isaacarthur.net. You can also catch all of SFA's episodes early and ad-free on our streaming service Nebula, along with hours of bonus content like machine monitors at go.nebula.tv/IsaacArthur. As always, thanks for watching and have a great week.